In this section, we will discuss how to solve so-called linear first-order equations. So they are of the form a1 of x dy dx plus a naught of x times y equals b of x. Now let's talk a little bit more about the terminology. So the fact that we're talking about a linear first-order differential equation, the linear part means that y and its derivatives show up to the power 1 only. You can't have a squared or a cubed or anything like that. And the other part, the first order part, that tells us that the highest derivative that we have is dy dx. Right? So this is our highest derivative. And note here that a sub 1 of x, a naught of x, and b of x depend on the independent variable only. So let's do an example where we're classifying differential equations as being either linear or nonlinear. So when we look at the differential equation here, we have y dy dx plus sine of x times y plus e to the power x plus 1. Let's see what goes right. So ex plus 1, we can call that b sub x. That's good. Then we have y to the power 1. That's good. And then sine of x, that's our a naught of x. And then we have dy dx that shows up to the first power, and that is all good. But now the part where it goes wrong is that the function in front of dy dx, that is not a function of x. We see that's a function of y. So this is a nonlinear differential equation. Okay, let's take a look at the next differential equation. It's in a slightly different form, but we have our dy dx shows up to the power 1, and then we can call this a1 of x equals sine of x, and then we have y to the power 1, and then cosine of x, that's our a naught of x, and then this function here, that is our b of x. And technically, when you bring the negative cosine to the other side, it becomes a positive cosine. So a sub naught of x is just the cosine part. So this is a linear first order differential equation. We're going to look at a very special case of this differential equation first. So I'm going to assume that a naught of x is a prime of 1. So that's a big if, but if that is the case, then our differential equation is very easy to solve. So again, that's a big if, that's not typically the case. So My differential equation looks as follows. I have a1 of x times dy dx. And then normally I have plus a naught of x, but I'm going to replace that by a1 prime. So I'm going to write plus a1 prime of x. So I replace my a naught by that. And then that's a1 prime times y, and that equals b of x. But what you should see here is that you have a function times the derivative of y, and then you have that the derivative of that function times y. Hopefully you recognize a product rule there. So what we can do here is we can write this as the derivative of and then I can write the inside as follows. I have a1 x times y. And that equals b of x. Okay, now how can we use that to solve the differential equation? Well, we have a derivative of something equals b of x. So to get rid of that derivative, we can integrate. So we start off with dx of a1 of x times y equals b of x. And now we're going to integrate both sides with respect to x. So dx here, integrate b of x dx. And what that does is the integration cancels out the derivative. And so on the left, we're left with a1 x times y. And on the right hand side, we have the antiderivative of b of x. Now, of course, when we do this, we introduce a constant of integration. We'll just bring that to the other side. And if we want to get y by itself, we then get y of x is 1 over a of x times the integral of b of x dx plus a constant of integration. So again, this is the solution to the differential equation only if a naught of x is a 1 prime of x. So what do we do when a naught of x is not the derivative of a1 prime of x? Or sorry, not the derivative of a1. It turns out that we can still use the product rule by multiplying our original differential equation by a suitable function. So to see what this function should be, we first put our differential equation 1 over here into the standard form. So what you notice is that we divided both sides by a sub 1 so that we have a leading coefficient in front of the dy dx. So p of x, we have that a naught of x divided by a1 of x, and q of x is b of x divided by a1 of x. Now, this is our standard form, and we're going to multiply both sides of this equation by a mystery function mu of x. Okay, so that's what we get. So we have our dy dx, and we're going to multiply that by our mystery function mu of x, and then we're going to multiply our mu of x times p of x, and then we still have our y here. And then on the right hand side, we get mu of x times q of x. Now at first that seems like a crazy thing to do because our differential equation just got more complicated. But it gives us a little bit more flexibility. So this is what we want to take a look at. Remember, we were able to find a solution if the second function in front of the y was the derivative of the first function. So we want to see, is it possible that this function is the derivative of this function? So is it possible to choose mu of x such that mu of x times p of x equals mu prime? So that's the big question, because once we can do that, we can do a similar thing like we did here. We'll be able to write our equation as a derivative of a product on the left-hand side, and we can find our solution. So we'll continue that in the next video.